Okay, now it should be fine. Could you cross check, Furkan? Yes, yes, yes. I noticed that I am muted uh, on the OBS studio. Now it should be fine. Could you please tell me if noise and is there any noise and is there any resolution issues? Okay, I think both are fine right now. Am I correct? Am I right regarding this one? Yes, I can see 4K resolution. And is there any noise? Is there some noise on my voice right now? Could you please tell me? Okay, thanks a lot. Then let me continue with our agenda. Yes, today we will be discussing actually content of the of our previous lecture. So we will have a fast recap regarding purpose of reset signals, reset code examples, reset architectures and infrastructures, and then finally some slides about asynchronous reset, synchronous resets, and not using reset comparison, of course, together with some of the pros and cons. And then the Q&A session we will be having. If you have any questions, please send them to YouTube chat box, chat window. Okay, the first one was purpose of reset signals. So as we discussed last Wednesday, so reset provides the initial value of sequential cells in hardware. So registers, in other words, flip-flops will be at known states after the device configuration. So this is what reset systems, reset usages provide us. And actually, the difference between resets and providing initial values is that with resets, of course, you don't have to reconfigure your system, but actively, while system is working, you can reset, you can set those initial values of some signals that are connected to your reset architecture on the fly. So this is the difference. You can configure, you can change those values, set those values to predetermined initial values in your code, which we will give some examples very soon, while device is working, while system is alive. So for the initial values, setting signal or variable initial value using that colon equals operator you see at the bottom, that sets those values only once, of course. So this is a difference. This is a actually this is one of the, let me resize my video a little bit. Yes, this is better. This is actually one of the questions asked after the Wednesday lecture. So those initialization is only once, of course. So when you declare your signal or when you declare your variable, those values are assigned to your signal or variable only once when during that declaration. So in order to get that value once again, you need to reconfigure your device. I mean, you need to load your bit stream once again. Otherwise, yeah, you cannot control those values without using such reset approach we are discussing right now. So next bullet was if an initial value is not specified. Actually, this is not specified case is also similar. So if it is not specified, it gets a default value, but it gets that value is only after that device configuration. So sequential primitives are assigned to a default value, but here we have an important note for flash-based FPGAs. Their behavior, which we will be explaining soon, is different compared to RAM-based FPGAs because actually this statement is not valid for flash-based FPGAs flip-flops because they are non-volatile memories and they are keeping, such flip-flops are keeping their values after last power off. So if let's say the value of one microchip, let's say ProASIC 3 FPGA flip-flop value was 1, and if you power off, and unless you have you don't have any resets statements in your code, and even if you specify an initial value, so that will be skipped, so that will be ignored. Probably you will be you are supposed to see that warning in your compiler. So those initial values are not applicable for flash-based FPGAs because they are behaving like non-volatile memories and they are keeping their last value before the power off, as I mentioned. But of course, if you reconfigure it again, if you like force a reconfiguration from the scratch after power on, then they will get those bit stream values again. But as you know, flash-based ones does not require does not require a reconfiguration or a configuration flash externally. So unless you force a bit stream load from the scratch after the power off, let me say after a new power on, then they will keep their previous values. So this is the behavior of flash-based FPGAs. You can test it in your lab. You can add some logic analyzers and see that they are keeping their values unless you use an appropriate reset architecture. Of course, you need to write those HDL code. You need to provide those reset statements. Also, you need to have a external resets incoming after that power cycle and resetting your flip-flops properly. You also need that. So writing, actually providing asynchronous or reset, asynchronous reset or synchronous reset statement, of course, is not enough. You need to have those signals physically resetting your flip-flops. So they need to be there physically. Of course, for instance, if it is synchronous one, it should, the setup and hold constraints should be fine because it's a synchronous signal. It's a synchronous input like any other signals read in your process. Those inputs shall be shall have positive setup and hold selects. And if it is an asynchronous reset, then you need to have that asynchronous assertion, synchronous deassertion behavior properly. Actually, then instead of for that one, instead of saying setup and hold, since asynchronous reset is an asynchronous control signal, then terminology is recovery and removal time because they are asynchronous inputs. Okay, in most cases for RAM-based FPGAs, that default value is logic 0. But there are some exceptions, some primitives. You can find more details regarding each family guideline. But sometimes, for instance, as illustrated before, for Ultrascale Plus family, Xilinx FDSE and Xilinx FDPE, those primitives, default values are not 0 but 1. And this default value can be changed for each register actually using EDA tool GUI, graphical user interface, or tickle scripting. As many of you know, each button we clicked, each and everything we do in graphical user interface of Libero, Quartus, and Vivado, those tools, also the similar ones, there is a tickle script equal of those actions. So anything you do using your GUI, it is possible to be done using tickle scripting in as well. Yeah, and in automated design and verification approaches, those EDA tool GUI graphical user interface are not preferred because tickle scripting actually that batch mode operation is faster, and since those CI/CD cycles, continuous integration, continuous deployment approach are like 90% of the time, 95% of the time are done on servers without any human interference. So tickle scripting is really popular. That's why I also told during Turkish FPGA Zero from Hero series, you are supposed to use your graphical user interfaces when there are some problems. Let's say you have a timing failure. Let's say you have a simulation mismatch, verification, functional coverage, or code coverage problems. So then you need to examine those problems with GUI in case it is necessary. Otherwise, opening GUI, doing everything by clicking, you add the human factor there, then possible errors, possible issues are coming on the table. So instead of that approach, like for more than I think 20 years, some good companies, well-known companies, popular ones, let me say, in terms of software, hardware, or firmware developments, yeah, they are using this scripting approach. Tcl scripting, of course, if you are using a Linux system, also that makefile approach are pretty popular. So you are combining makefiles, make approach, and Tcl scripting. In addition to those, you are using, let's say, Git as versioning management tool, Jira as task management tool, and Bitbucket as CI/CD tool. Then combination of these three tools plus batch mode design and verification, it becomes really extremely powerful and extremely shortens development cycles compared to those human clicking GUI approach. So that's an important general advice. But last bullet was regarding you can change these default values for RAM-based FPGAs. They are not supposed to be 0 all the time. If you would like to have a register with, let's say, with walking zeros, let's say, at the beginning, thinking that it's a vector, you can make it, let's say not walking zeros, but let's say 1 0 1 0 1 0 kind of vector. You want something like that, or any counter value for a 32-bit vector. Let's say you would like to start after device configuration. Then you can do that using Tcl scripting or using assignment editor of Quartus, let's say, and similar tools exist in other electronic design automation tools as well. But this is different from that providing initial values inside the code. This is also possible. As I mentioned, after signal declaration, there are some examples as well in following slides. You can use that colon equal approach for signal value or variable value signal or variable default values after that device configuration. In other words, after FPGA loads the bit stream using JTAG or some similar interfaces. Okay, here we have some code examples. Let me check if we have any questions right at this point. You can also shoot them on the fly while I am having the simulation. Actually, this is a primarily Q&A session, but I am doing the recap because we right now don't have any questions. As long as you have questions, I will stop the recap and answer the question. Okay, code examples, reset code examples. So on the left top, we see a synchronous reset using VHDL. I explained in more details way last Wednesday. Let me a little bit mention it faster. As you see, since it's the synchronous reset, there is no reset signal in the sensitivity list. So after if rising edge clock, you are starting another if statement. So it is like you see a nested if. You are increasing that dependency because rising edge of clock, since it is synchronous, you need to have the rising edge of the clock first. Then, like any other synchronous inputs that you use in your process, you use this reset underscore 400 megahertz signal and check since it is an active high one. If it is 1, then you are resetting your signals, and after this else, you are writing down your codes. Your logic is here, but keep in mind that of course there will be some other if statements, some case statements, some other logics inside this part, but you are not supposed to reset each and every signal here in after that active high reset. Resetting only signals that are in your control logic, that are important for your FPGA output pins or internal software dependencies. They are supposed to be reset here. So if you add each and every signal you declared in this entity of this process, then you are wasting kind of different resources. Like we are wasting some routing, global routing resources. Sometimes not global, but some local routing resources. Also, you increase the power usage, and it may result also in some timing problems. If it is synchronous one, Fmax is getting lower. Most of the time, if it is asynchronous one, it may result in some negative recovery and removal slacks. Actually, most of the time, the asynchronous one results in negative recovery and removal times. The synchronous one is resulting in negative setup and hold slacks. So this is the difference. Just the name of the timing parameter changes. One is if input is synchronous like this, we call setup and hold slack. If we are considering the asynchronous inputs, then we are saying it's recovery and removal slack. Okay, this example is for the synchronous one. Asynchronous one, since now having that reset has higher priority, then you have that reset underscore 400 megahertz signal in your sensitive list, and since it has higher priority, your if statement start with if reset statement, and then you reset again any signal you are supposed to reset, not each and every signal. Then else if rising edge clock, you are providing your logic. So you see here there are 2 level if statements. but here there is only one. So there is only one endif, as you see. You can cross check from the endif statement as well, but here you are you have two endif statements. So this is the difference. But in order to use this asynchronous reset properly, you need a reset synchronizer. Let's say you have this reset active high reset signal you see on the right bottom is coming from the FPGA pins, FPGA ports from an external reset IC. You need to synchronize this one each and every clock domain you have in your design. If it is a asynchronous reset, then you need to use this kind of reset synchronizer. Of course, number of flip-flops may change depending your process voltage, temperature, and clock speeds. PVT of the FPGA you are using and clock speed you are implementing, let me say. You may use triple flip-flop or quadruple flip-flop solutions. This one is the simpler one, two flip-flop solution. But similar requirements applies if this reset is synchronous, like this one. Let's say you see in this example. Actually, let me add reset synchronization, reset two flip-flop solution to this one as well, this synchronous as example as well, so that here in this one, this reset underscore 400 megahertz is completely synchronous to this clock domain. As you see the suffix here, both has that underscore 400 MHz ending. So these are completely synchronous. But if you would have the same scenario like this, the resets only that RST signal incoming from your FPGA pins, then not reset synchronizer, but this is a reset synchronizer circuit because it is different compared to a single bit, double, triple, or quadruple clock domain crossing solution. This is different. But here you would use, let's say PVT and clock speed is enough, is not that strict, and two flip-flop solution is possible in synchronous scenario. Then you would use another process, and if rising edge, similar statement actually. You would start with if rising edge, again the clock underscore 400 megahertz, then but you would assign this reset input here to another flip-flop, and the output of that flip-flop, let's say you would write, let me write here with we have a digital pen. Just a second. Okay, so you would do something like this for generating that RST underscore 400 MHz input, whose source is coming from FPGA pins. Actually, asynchronous, directly asynchronous to clock, 400 megahertz clock we have on the left. So you would like something like you would write again let's say P underscore 2 FF CDC resets. Let's name it like this. So process, let me just a second do this. Yes. Let me put okay. Let's do this. Let's remove this, change the color. Okay. So then, oh, is this the other slide? Yes, I switched the other slide. Let's start from scratch here. Yes. Then it will be P underscore to FF CDC RST. Our signal is RST incoming from FPGA pins. Then process clock 400 MHz is begin if rising edge clock 400 MHz, then now you need to flip-flop, since this is a 2 DFF solution, 2 D-type flip-flop solution for clock domain crossing, this reset signal. You can do, for instance, something like this. Reset D1. Okay, where is the equal sign in this keyboard? Just a second. Oops, this is unfortunate. Then let's do it like this. It will be faster. Actually, let's write this statement in C++. Sorry, in Notepad++. Actually, where is that reset examples one? Okay, let me a little bit zoom it. Then let's write it from scratch here. Okay, Furkan has some questions. I will answer them shortly. Let me write the clock domain crossing code of this synchronous reset we are using on the left. So it will be something like this. I think it is. Yes, I think we are good. So, okay, now it will be P underscore. We are labeling the process to FFCDC reset. The signal is reset, so we start with process sensitivity list only clock. Oops, sorry. Is. Then you have the begin. Then you will have the if rising edge clock 400 megahertz. Then reset CDC. You assign, you use first flip-flop for clock domain crossing. Then you will have this RST underscore 400 megahertz assigned to this reset RDC, CDC. So, and then your end if, and then your end process he underscore, oops, okay. So this one actually, in case I am mentioning again, 2 flip-flops are enough to apply clock domain crossing for their RST signal, and MTBF is still high enough, more than, let's say, 70 years still, using 2 flip-flops. But in case your PVT value, yeah, depending on your PVT values, and we have that 400 MHz clock here, you may, let's do the triple flip-flop example, because that reset synchronizer for asynchronous one, we also use 2FF solution. Let's use triple one. It is actually, again, simple, but we will just use some additional suffixes, and we will assign, connect these output of these flip-flops to input of others for one more time. So this is triple flip-flop solution for clock domain crossing this asynchronous reset signal into 400 MHz clock domain. So we are assigning that reset signal incoming from FPGA pins, one of FPGA pins, and then we are registering it. Output signal name, output of first flip-flop is RST underscore CDC underscore 1. So we are assigning it to input of second flip-flop, and of course output generated by the second flip-flop will be connected to RST underscore 400 MHz. So then you can use, since this signal is synchronized to this 400 MHz clock domain, now you can use this signal on the left as a synchronous input in this process. So this is the proper way. I will also add this part to the presentation after this lecture. So yeah, here I assumed that RST underscore 400 MHz is already synchronized to this clock domain somewhere in the design, either in this entity or preferably incoming from top level. So, but this will be a good sign the ones starting FPGA design, FPGA design and design or verification. So for the fresh FPGA engineers, this will be a good example. This is straightforward actually, but you have to have this, otherwise you will have some metastability problems, because setup and hold time for the synchronous reset example, you cannot meet setup and hold time because this reset signal is asynchronous to this clock domain. Similarly, you need to have this reset synchronizer for asynchronous reset, but as you see, it is a little bit different because type of the circuit is different. Let me draw that one as well for beginners. This is a good example as well. So for the clock domain crossing, let me change the, okay. And also I need a little bit tinier. Yes, this is better. So for the upper one, your circuitry is something like that. You have 3 flip-flops, so those clock inputs are connected to this clock 400 megahertz. But from, let's say this is the whole FPGA, and from one of those ball grid array pins, let's say it is not ball grid array, but it is the traditional previous technology, because then it could be, drawing could be misleading. Yeah, let's say this is the FPGA, and you are getting that reset signal from a reset IC here. Okay, so this is the reset signal, RST. So you are providing for this clock domain, clock underscore 400 megahertz. You are like we did in this example code. So you are connecting reset. So this is the register of reset underscore CDC underscore 1. So this is underscore 1, this is underscore 2, and this is the that reset underscore 400 megahertz flip-flop. So this signal, the output of this flip-flop is exactly this reset. Let me reset underscore 400 megahertz. So this one is just synchronizing with triple flip-flops, and at the end, metastable, of course, depending on your PVT values and your technology, values incoming from the FPGA you are using, plus this 400 megahertz, you can there are some nice calculation tools. Of course, you need to provide 3 parameters from your FPGA device datasheet. Then you can calculate the MTBF value of this. Actually, this signal after those 3 flip-flops could still be metastable, but that MTBF value, mean time between failures, like really high, really long. It is like more than, let's say, 70 years. In case it drops to 1, 2 years, 3 years, then you need to add another register in order to again extend that MTBF value. So this is the logic behind for clock domain crossing of single bit signals, signal bit signal, or as let me say signal bit signal. It is, let me don't make it confusing. But here approach is a little bit different. So you have, now we apply we use 2 flip-flops, and since it is active high reset, you need to connect this data input. This is clock, and asynchronous reset is connected to this reset for both flip-flops. And yeah, this is the clock, same clock actually. I won't write the name. So this one, clock underscore 400 megahertz. But here you are connecting it to ground. This is ground. So 0, G and D. And then you connect output of first flip-flop to other. And this is, don't be confused. The signal names are the same. But for this example, RST underscore 400MHZ is this one. And actually what you are doing, in case this reset is the external reset incoming from an IC, in case it is active, and it is active high one, as you see, that reset assertion during the active time of that reset, when it is 1, the outputs of those flip-flops are also assigned to 1 asynchronously. So as long as you get this 1, the output of this queue of this first flip-flop and Q of output of the second flip-flop, they are both 1. But during the rising edge of the clock, when that reset is not active, during each rising edge of the clock, output of first flip-flop is assigned to 0. Actually, this one will be 0, and next clock cycle, this reset underscore 400 MHz underscore pre is assigned to our output. So since the first, in this example, again considering that PVT is good and 2 flip-flop is enough for this reset synchronizer, there is of course a probability of having this first output metastable, because that reset underscore 400 MHz underscore pre is changing its state from 0 to 1 when it's going to rising edge of the clock. And of course, since that reset signal is asynchronous, you cannot guarantee that the setup and hold slacks are positive for this first flip-flop. So this could be metastable, but having this second flip-flop here, the output of second flip-flop will be like metastable in once per, let's say, 70 years, 50 years. Then it is okay to use 2 DFF solutions. Again, if your FPGA family is like an old one, and by the way, if it is old, too old, it won't be possible to use a 400 MHz clock anyway. So then actually for that FPGA, if tool cannot provide a positive slack, any positive slack for 400 MHz, you will anyways won't use it. But there are some cases that FPGA is capable of providing positive slacks for, let's say, 400 MHz, but still MTBF using 2 flip-flops is not that good. It is like 1, 2 years, 3 years. Then you are adding the third flip-flop, and actually you are doing the same thing we did, making this one third with 3DFF solution. So it is straightforward. Then you will have then pre underscore 1, you will assign pre underscore 1 to pre underscore 2, then pre underscore 2 to this output signal. Then you can use, after this one, you can use this asynchronous reset. But asynchronous reset timing issues, the problems is a little bit more complex compared to synchronous reset you see on the top, because okay, you may provide this reset synchronizer, but now in addition to setup and hold checks, you are now having also recovery and removal checks. So because you have this asynchronous nature signal in your code, now you will see if you do this kind of coding, your EDA tool will be providing you also recovery and removal slacks. If you don't use any asynchronous reset, if you don't use any asynchronous control signal, actually you won't have any recovery and removal timing. But there are of course pros and cons. If you use only synchronous ones like this, of course we will discuss, this is also depending on your FPGA family. If there are some built-in resets, built-in asynchronous resets, it sometimes makes much sense to use them. But also some families have synchronous built-in resets. So yeah, it depends on many things, but one of the major drawbacks, which I will cover at the end, if you don't have built-in synchronous reset inputs, then this type of approach consumes one of those lookup table inputs. Let's say you have a 6-input LUT technology, one of the newest ones. Then if you code like this, actually that lookup table will behave like a 5-input LUT, which is an older technology. So each and both asynchronous and synchronous resets have some pros and cons. Actually, best cases, as I mentioned during the previous lecture, avoid using resets as much as possible. If it is some internal signals or your design, if resetting a signal is not providing any pros for you in your design, you need to consider them, and you shall not reset those signals after your reset statements. This is the approach. For instance, there is a nice example regarding that. If you have in your process, if you have a state machine, then with resets, you can reset only your state machine and a few important additional control signals, if there are some, and then you will be forcing your state machine signal to go to an idle state, and in that idle state you can reset some other internal signals that has second priority to be reset. So instead of resetting all, like in total 1,000 registers, you can reset just, let's say, 20 of them, and then depending on the necessities, depending on your second, third priority of resetting a signal, you may reset those in your idle state. That is a good approach, for instance, good coding practice. Then you will be optimizing placement and routing, actually, your resources, and you will improve your maximum frequency, Fmax value. Okay, this one is actually the most preferred case. Unless you don't need it, don't reset the signal. Like this one, for instance, this is some internal signal. So in case you are not fine having all zeros, assuming that this is an RAM-based FPGAs, you can also set some initial values. As I explained at the beginning of this lecture, this colon equal signal sets the initial value, but keep in mind that this signal will get this value after new bitstream load again. So you cannot control on the fly while code is running this reset, but this is just the initial value for after device configuration. This is also good. This could be enough. Most of the time, let me say, this kind of initialization is enough for internal signals in your component, in your entity. Here we gave an example regarding making most significant bit of this logic vector 1 and other bits 0, and we just registered this value to my underscore signal defined here. That was, we used that tick range attribute such that this is that STD logic vector, standard logic vector, whose size is like this input underscore 1 signal. So this is also, and automatically the size of this logic vector will be data width minus 1 down to 0. Also, here you see that tick left, so most significant bits of since their sizes are the same with input underscore 1, so most significant bit of this my signal will be assigned to 1 after device configuration as the initial value. Okay, so we provided some details regarding reset architectures and infrastructures. Let me read each bullet. Vendors recommend to take special care in deciding if the design requires a reset. You need to design reset architecture very well, otherwise it will result in many design and verification, optimization, and or complexity issues. In many situations, resets are only required on the critical control path logic for proper operation, such as finite state machine signals, clock enabled, data valid, and critical output signals. Not each and every entity you are using as a component in your design, not each of those outputs are directly affecting your FPGA output ports or any critical logic. So you are not supposed to also reset, let's say, huge standard logic vectors outputting, actually going out from your entity as well. But you need to provide some good comments saying that I didn't no reset value for this signal since blah blah blah. So you need to explain that. Otherwise, your colleagues, your future colleagues that will be using your designs will be confused, and since maybe they don't have enough experience regarding that, and they will add those signals into all of those resets under that reset statement, and they will waste some resources, or they will lose time considering why reset values are not provided for those signals. So use some strong comments. Also explain such things, such optimizations in your documentation. Then it will be really informative and helpful for your team, for your company, for future purposes. Next bullet, flash-based FPGAs require additional attention since their flip-flop does not start from 0 like RAM-based FPGAs, but start from last value they got just before previous power off. Yes, this one is important, as others I mentioned. Also some mission critical signals or potentially dangerous hazardous signals. Check the figure on the right. This design assurance guidance for airborne electronic hardware, that DO254 by RTCA committee. So when that design assurance level is level A, it is catastrophic. So then you are taking some extra precautions such that that catastrophic scenario will not occur. Like I gave a laser designation signal, for instance. Even if the clock in your design is gone somehow, you would like to stop it with an asynchronous reset. Synchronous reset will not work. Let's say if your clock is somehow, clock circuitry, clock IC is somehow gone, I mean not working, because synchronous reset requires a rising edge of clock. If you somehow cannot provide a rising edge clock, then of course in case of an emergency you cannot stop that critical signal. Then laser designation will continue, and as you may guess, it is dangerous. There are some eye-safe ones as well, eye-safe lasers, but for distance measurements, laser designation with some guided bumps, those are most of the time they have huge power and they are not eye-safe. So during laboratory tests and while using during some operations, it is preferred to stop them in some emergency cases. Of course, there are in labs also some emergency buttons that cuts down the power of everything, etc. But keep in mind that those stuff has some huge capacitors as well. So stopping the power sometimes does not shut it down immediately. So some extra precautions, measurements are taken as well. Also for those flight controls, they are really critical because, yeah, you know, as a it may result in some crash, deaths, etc. So extra measurements are taken. Let me say, majority voting is one of good example regarding that one. Most of the time, instead of providing a one flight control system, they are adding triple, and they are checking the results of they are looking the results of majority. So let's say you have 3 exactly same flight control systems, flight control computers. They are not huge, by the way. They are in size optimized as well. So if all 3 is giving the same outcomes, it is the best. If 2 of them are giving the same result, same results, let me say, you are still trusting, but each giving different, each 3 is giving a different result, then this is also really bad, because you cannot trust. You don't know which one to trust in that case. But yeah, there are some also additional requirements, additional algorithms running to avoid such problems. Okay, next one was second slide regarding the reset architectures and infrastructures. EDA tools that detect clock domain crossings, CDCs, have become a standard quality check into today's design space. To be honest, very few companies in the world still using these clock domain crossing tools. You can do some analysis with Quartus and Vivado or other tools as well, but these clock domain crossing tools are really expensive, and they are providing much more complicated analysis. So yeah, but since there are also really let me say economically strong companies in the world as well, so they have some of them are purchasing these tools and using those in their CI/CD cycles as well. But to be honest, it is the most sophisticated ones are quite expensive. But newer to this game, RDC tools are reset domain crossing verification is also now on the field. So improper reset domain handling can cause the metastability issues and unpredictable behavior as clock domain crossing errors. As an example on the bottom right, a reset domain crossing RDC issue in a design with asynchronous resets. For instance, in this design, maybe asynchronous resets are preferred because the technology has built-in asynchronous resets. If you have that built-in pins in your flip-flops, then of course you are saving lots of resources because they are there in that ASIC design. Those reset pins are provided. Many Altera families like Stratix 5, Cyclone 5, Aria 10, Cyclone 10, for instance, and some older ones as well, they have built-in asynchronous resets, both the flip-flops in their ALMs, adaptive logic modules, and preliminary pre-registers and output registers inside digital signal processing units. they have that asynchronous reset, built-in asynchronous reset. So for instance, for such families and some similar families, it really makes sense to use asynchronous reset most of the time. As I said, by the way, that not using is still there. As long as you that signal you defined does not require an immediate reset value, you are not supposed to use reset. But I am mentioning here, in case you need that reset value, then you need to check your FPGA family and you need to check your resources. That is the approach. So here on the bottom right, for instance, there is one clock domain, two flip-flops, both has the same clock domain, but their asynchronous reset signals are different. There might be many different scenarios ending up with this, but one example let me give. Let's say you synchronized your clock using the approach I illustrated a few slides before here, like this. But since this is 400 megahertz, so clock period is only 2.5 nanoseconds. So it is tough to meet that setup recovery time especially when fan out of this signal is really high. Let's say it is more than 1,000, or sometimes it happens actually if you use it extensively, it is becoming more than 5K or more. Then you are getting negative recovery slacks most of the time, and then you need to clone this reset synchronizer. So you need to do two different reset synchronization. In this scenario, so then you cannot guarantee, if you are using that duplicating reset synchronizer circuitry, then you will reduce the fan outs, and most probably if your FPGA technology is also enough, you will get positive recovery slacks. But now you cannot guarantee these two reset signals are getting their reset values during the same clock cycle. For instance, then if this reset is applied to the first flip-flop, and let's say, as you see here, output of this first flip-flop is used as the input of the other flip-flop, then resetting this will change the state of this output of DFF1, and setup, since this DFF2 is still actively working, asynchronously resetting output of DFF1 will result in setup and hold problem for DFF2. Then output of this DFF2 would be metastable, and this may be used by some other processes, other logic elements, and then your design may start working inappropriately, in a wrong way, and it may result in some catastrophic, some bad issues, let's say. So this is an example. And this last statement is really strong. Applying, again I am mentioning, applying asynchronous or synchronous reset to all the signals in entity is a big waste anyways. As I mentioned, you need to check your vendor technology, your FPGA device guidelines, and you need to be aware of if you have built-in synchronous or asynchronous resets. then you need to, in case you have to use resetting, then you need to pick the one you have built in. If you don't have both, then you may discuss selection depending on, again, your FPGA family, your clock speed, etc. Because using directly, for instance, synchronous reset is good, is preferred by Xilinx. For instance, Xilinx recommends to use synchronous resets as long as you need a reset, but it also has some drawbacks. It is using that one of your lookup table inputs, and it is decreasing maximum frequency, for instance, since it increases total resource usage, and it has like routing congestions effect, power usage, extra power usage effects. So yeah, you need to make some tables, compare and contrast. You need to check your compilation results, discuss those details with your team, and take your actions accordingly. So in summary, avoiding the unnecessary use of resets limits the overall fan-out of the reset net, reduces the amount of interconnect necessary to route the reset, usually global routing paths and global set resets, simplifies the timing of reset paths, and reduces the total static timing analysis effort. Since effort is less, also total time you wait for the compilation will be less. So it reduces total STA effort and time. And finally, those results in most cases overall improvement in performance, area, and power usage. So you are winning a lot if you avoid the unnecessary use of resets. I mean, you can still use some resets, but here it is mentioning not resetting each and every signal. So if you don't have these effects, if you have some reset signals but their fan out is quite low, then you will not suffer from these dramatically. Its effect will be really slight. But otherwise, if you have, let's say, 7 clock domains, and each clock domain reset fan out is more than 1,000, then you are getting some bad effects in terms of performance, in terms of area, and in terms of power usage. So resource usage, getting a lower Fmax, getting some actually even negative selects, of course, depending on your constraints, negative setup, hold, recovery or removal selects, and of course power usage is also increasing. As I mentioned, preferring synchronous or asynchronous one depends very much on the specific vendor and family. So there are some nice good examples here. In terms of slice or flip-flops, Xilinx call those slice, Altera calls these ALMs, adaptive logic modules. There are some, I provided some register examples, slice ALM register examples for some Xilinx and Altera FPGA families. Xilinx Vertex 5, 6, 7 families have slice registers with both built-in synchronous and asynchronous reset pins. But note that majority are synchronous. Altera's Stratix 5, Cyclone 5, Cyclone 10, Aria 10 families have ALM registers with built-in asynchronous reset pins. These are for slice/ALM registers. But for DSPs, it is different. Xilinx Vertex 5, 6, 7 families have DSP registers with built-in synchronous reset pins only. Altera Stratix 5, Cyclone 5, Cyclone 10, Aria 10 families have DSP registers with built-in asynchronous reset pins. So then your optimization, your coding is changing not only depending on the vendor, but also depending on the family as well. Because Stratix 10 families, for instance, have DSP registers with built-in, let's say, synchronous reset pins. There are some that new architectures also have some registers, flip-flops, without any resets. So yeah, you need to check family details, cross-check them. You need to check their documentation, design guideline, and you need to do your coding in a generic way, such that you have some generics regarding your vendor, Xilinx or Altera or Microchip or the other ones. And also, this is not enough. You need to have some generics regarding the family. And then using generate if statements, you need to optimize your design depending on those generics. Otherwise, for some families, your design, if you use a common design for each different vendors and families, then it could be optimum for some families, but it will be really resource weight, suboptimum, actually not optimum for some other FPGA vendor and families. This is really important. If you would like to benefit strongly from design reusability, and if you would like to improve the visibility of your designs, the code quality of your designs, you need to go with such strategies. Otherwise, yeah, you will be either writing some codes for each project, for each task, because you are not reusing those previous know-how of your company, or you will use a plain VHDL code inference, but it could be, if you don't use such generics for vendor and family, then your design will not be optimal. So you will use more resources and your timing performance will be worse. Okay, I think this one is clear as well. So I think this was the last one. Yes. Another slide regarding asynchronous reset versus synchronous reset versus not using reset. Using asynchronous reset brings recovery and removal time issues, since you are using asynchronous control input signals, additional metastability problems, potential reset ordering problems, as we see that cascade resetting issue in that RDC slide. Actually, order of those reset matters a lot. You need to take additional care regarding those. Glitches may result in reset easily, yeah, because the reset is asynchronous. Any tiny slide that your flip-flop technology will see, that tiny glitch will capture that tiny glitch. Let's say your technology captures identifies a signal as a reset, let's say if it is 30 picoseconds high, and let's dream reset is active high. Then if that 30 picosecond signal may result in asynchronously resetting all your logic. This would be a huge problem. So that noise level, then EMI/EMC problems may result in some other kind of interferences, digital interferences, RF interferences may result in your circuits, your logic, your processes are reset. Using synchronous resets brings wasting one input of LUT and then timing closure Fmax issues. Also, yeah, that fan out of synchronous reset could be really high as well. Also, that is also brings actually routing problems as well. So as long as it is possible, avoid increasing fan out of your either synchronous or asynchronous reset signals. I mean, don't use them as much as possible. Don't add signals under your reset statement as long as it is not a must. Therefore, a conclusion here, unless you know FPGA family, technology of your FPGA family, and unless you design accordingly, if you are using as asynchronous reset, a reset emulation circuitry will be applied. So this is a waste of resources. Also, as I said, that if fan out is high, then it will be ending with some routing congestion, some routing issues. When fan out is high, actually you are wasting some global resources, global routing resources, and the connectivity issues, etc., are coming on the table. If you are using a synchronous reset, then one input of your LUTs with related signal is consumed. So all in all, those are some huge hazardous resource wastes. So try to avoid from them. Okay, Furkan told me that we cannot see the drawings of asynchronous part. I think I fixed that. I got my answer when you write the last process at Notepad++. Thanks. Okay, but let's mention your question again. Maybe some people will realize now. At reset synchronization process, RST signal, internally generated signal passed from flip-flops, or we use external. Yeah. By the way, it could be incoming internally from a different clock domain, Furkan. Then you need to apply the same thing again. Yes, actually you asked, nice point. You are saying don't use external signals directly before synchronizing them. 100% correct. You cannot use any signal, even if it is an asynchronous reset. You are not supposed to use them before synchronizing them, because synchronous reset is also proper when reset assertion is asynchronous, but reset deassertion is synchronous. So you need to use that reset circuitry. For the synchronous one, you need to use that double flip-flop, triple flip-flop, or quadruple flip-flop clock domain crossing solution. I think those are clear. Let's go to the final slides. Any other questions? Actually, I tried to make it quite self-explaining. I also answered some questions that some may ask through the presentation. I think we are good, and we may end the stream. All right, great, clean and clear. Thanks, said Furkan. Thanks a lot, everyone. I would be happy if you like the stream, if you are watching it now or when you watch it later. Thanks a lot. Have a nice Sunday then. Bye bye.